Good morning, guys. Thank you very much for showing up this morning. I know it must have been a very hectic week for you so far, and the evenings have not been any less interesting. It's New Orleans after all. So again, thank you very much for showing up. We are going to talk about Hyper-V storage architecture, what makes us tick, what is their performance improvements, and so on. Let's see. My name is Matthew John. I am the Group Program Manager for Hyper-V, and with me here is Liang Yang. You want to talk, Liang? Introduce yourself.
Hi, hello everyone. I'm Performance Engineer at the Hyper-V teams, so my primary job is to make sure Hyper-V delivers the best performance in industry.
Excellent. So today we are going to talk about the storage architecture. What does Hyper-V mean? How does Windows work? We're going to go through some of the block diagrams that people think are geeky, but it will help us understand a bit about how I/O flows in Windows in the Hyper-V stack. We talk about our ongoing investments in storage. We also talk about what are we finally recommending to our customers if you're starting from scratch. So let's quickly go through it. In terms of Q&A, I am actually okay if you guys decide to ask a question right while I'm presenting or while we are talking. But if the answer would take longer, I would gently defer you to the end of the session so we can have a private talk. And Liang and I will both be here after the talk to be able to answer any questions you have. And with that, let's start. So you have to apologize. I am going to go through a series of block diagrams that might appear really geeky and quite detail-oriented. I think it's useful for all the folks who use Hyper-V and the storage to have a basic understanding of how I/O flows. And at the end of it, if you guys get what I'm trying to tell, like it took me about 4 years to even understand how I/O works, so I'll be super amazed. So don't feel that you have to learn everything as we are talking about it. This might be something that you might have to come back and repeat or go back to your Windows internals books to read more about it. So the main thing that we're going to talk about here is how does I/O flow in Windows, and how does that affect I/O flow in a virtual machine. So let's start with the simple story. Everything that we are building is to help run an app. It doesn't matter what you're trying to build, the infrastructure. Finally, the application is the king. And the app, the main thing it wants to do is write to the disk. So let's see, how does it do that? It starts by writing to the file. Very simple. Great. Where does the file live? The file lives on a file system, NTFS or REFS in our case, and the NTFS file system is built on top of a volume. The volume lives on partition. Pretty simple stuff. The partition lives on a disk. Then the disk can be surfaced using a SCSI or a SAS controller or an IDE controller for those of us who have been in the industry for a while. SAS, SCSI, you can have multiple disks attached to it. You could also have fiber channel or iSCSI connected to it, and each of those can expose disks. Great. Fiber channel or iSCSI implies that the disk is not living on the host, it's living somewhere else. So you go through some sort of a cloud, either a fiber channel cloud, a SAN cloud, or an Ethernet cloud, and it keeps building on it. And there's a SAN target at the end of it. Excellent. You could also have a file server that's handing off, or the files are living on a file server. The file server implies that the file is kept remotely, but instead of block storage, it's file storage semantics. And the file is actually residing on another remote box. In our case, we call it the file server. This could very easily have been a NetApp box or an EMC box that doubles up as a file server as well. So in our case, we have the RDR and the SRB on the remote end. And I just put in SMB 3.0 in there because, hey, we are very proud of that. So we have SMB 3, we have RDMA and multi-channel with SMB 3. So all that to give you extra power. And the SRB now builds on the existing storage architecture that we just drew. It sits on NTFS, it sits on SAS drives, and it can connect to a SAN on the back end. Great. So here's so the thing that I want to highlight here, while I called out SMB, you might want to go call out the file server guys. I think I've heard this, that the NFS file server or the SMB file server is also one of the best performing NFS file servers. We don't take pride in that apparently, or we don't go out and announce it to the world, but apparently it's really good, and this is some information that I didn't know about. When I talk to the file server team, I get to know about it. The other thing I glossed over is dedupe. Now, you probably have heard a lot about deduplication throughout this whole conference, so I'll keep it to a minimum. We'll get to one aspect of dedupe later on in the slides as I touch upon it. So the other thing is this particular file that the app is writing to can also be on a clustered shared volume. And these are where the concepts of clustering are coming in, where you are writing to volumes that are shared across multiple hosts. Now, the interesting thing is the CSV integrates into the Microsoft storage stack. So it uses NTFS and volumes and partitions, and it just blends in. And it enhances whatever capability we have added. And this will be the recurring theme that you will keep hearing throughout, which is we add technology that takes advantage of everything else that we have already built on.
It's not here.
Oh, sorry. So we had CSV, and now we talk about what else can we add. So we just added, what did we add? Spaces, thank you. So Spaces was a new concept that we introduced in 2012. Spaces, what it does is it creates a virtual disk based on your local physical drives. It again builds on top of your SAS SCSI controllers. It exposes a virtual disk or a space. Based on that, the space can be mirrored. And the rest of the stack, the rest of the file system partition stack just flows through, and the file just gets written to Spaces. So you get the added advantage. Now, Spaces can also be cross-machine as well. So you can have shared spaces. And for that, you have a concept called the JBOD that's brought in, and shared JBOD at that, which allows the spaces to be spread across multiple machines. You can have CSV on top of it, and you can build a shared cluster without needing any expensive SAN at the back end. So the JBOD provides the shared SAS capability, the shared storage, and Spaces provides the converged namespace for all the storage. If you notice, the minute I added Spaces and JBOD, my file server added that line called Spaces in there as well. So now my file server is able to take advantage of Spaces and provide the same capability that was available on the physical system. So, did it transition? There you go. So, now let's talk about virtualization. So far we have not talked about anything on virtualization. Let me turn on Hyper-V. And what happened? The hypervisor slipped under Windows, and we have created a partition called the host partition. It's the exact same Windows that we have known before Hyper-V. Nothing changed. The entire stack remains the same. We have just slipped a hypervisor under it, and the partition that we have created, we call it the host partition. It's just a special name. So how does that work? And this is where things get interesting, in that the advantage that Microsoft has, I'm just taking a detour here, about being able to leverage all the technology that we have built in for the last 30 years into Windows operating system. Now, this particular point I want to emphasize a little more. I've had numerous conversations with people who keep telling me that, you know, your operating system, it's old, it's not the right one. Virtualization should be separate. It should be something different from the operating system. And we go back and say, no, it is just part of the operating system. It does all the functions of what an operating system does. It takes care of your devices, it takes care of your I/O, it does scheduling, and that's what an operating system does. We believe that's part of Windows. Now, the other interesting thing about being able to leverage the 30 years of experience of virtualization is that, of Windows operating system is that it's all about bugs. Now, I shouldn't be talking about this, but any of you who actually write code realize that no code is bug-free. And that's where folks like us come into the picture. We can go out and keep advertising to the world that we have the best software in the world. But the reason why we believe we have the best software is not because we can write perfect code. It's because we have experienced, thanks to you guys and thanks to our own internal testing, the level of complexity that our software can introduce and the deployment complexities that you guys can bring in. You guys are able to configure and set up and deploy Windows and any kind of installation in so many different ways that it's impossible for any software product developer to be able to simulate, test it at the right conditions. And that is what we call as being reliable. We have the experience, we have the benefit of having seen those bugs. The system that we have and that we are leveraging right now and continuing to build on actually takes advantage of those years of experience of having found and fixed those bugs. Taking a bit more detour. When we feel very proud that Azure now uses Hyper-V, it's for the same reason. It's those millions of virtual machines that are running on the Azure cloud that runs on Hyper-V that gives us the wealth of information in terms of bugs, in terms of, hey, did you ever know that when you have this kind of a VM doing such an operation on one of those partitions while there's another 4 virtual processor VM doing something entirely different, our system behaves in a slightly different manner where the performance dips for a couple of seconds. Cool, we never knew that. Let's go figure it out and we find some minor tweak or bug that we get to fix. So anyway, coming back to this, that's the power that we have when you have virtualization, Hyper-V, all integrated as part of Windows. So we just, back to the story, we just created the host. Nothing has changed other than the fact that now it's virtualized. We have a virtual machine now, so we can create a number of virtual machines. And in each of those virtual machines, what do you have? You have an app that wants to write to a file, that needs to write to a file system, build on a partition, build on a volume and partition and disks. Looks pretty similar, and there you go, reuse. Now, that partition is running on disks that can be iSCSI or SCSI or fiber channel, or it could just be a local IDE drive. Now, notice one thing. I added a couple of words called synthetic in there. And that's one of those key differences between what happens in a virtual machine versus what happens on the host. It's synthesized. Now, IDE is not synthesized. So it is one of those devices, a legacy device that we actually emulate. So let's look at what the emulation looks like. So IDE goes to the hypervisor. So any disk operation that comes to the IDE goes through the hypervisor into the root partition, and it talks to the store VDEV. If it were a synthetic application, a synthetic drive device, it talks to the synthetic VSP, the store VSP or the fiber channel VSP, and that has a direct connection to the host using the virtual VM bus. And VM bus is one of those things that we have continuously tried to improvise and make it highly performant using multiple channels and so on, and we'll talk a little bit about that as well. So the fiber channel VSP, it talks to the fiber channel VSC. The fiber channel VSC requires a physical HBA, fiber channel HBA to be present on the disk, which supports NPIV. And it's with NPIV that we are able to get the disks connected to the virtual machine. It looks like fiber channel inside the VM, but it's a Microsoft HBA that shows up in the virtual machine. In the case of SCSI, it goes to the store VSP on the host, and the store VSP comes and talks to the VHDMP, and that's our parser. The VHDMP parser is the one that understands how the VHD file is organized and the VHDX file is organized. And you know what? By the time it gets to VHDump and it's writing to a file, the file is a manifestation of the disk on the upper end, but on the lower end, it's just a file. So it sits on the file system. It could be on CSV, it could be on SMB, it could be on local disk. That local disk could be a spaces disk, it could be a file fiber channel disk, iSCSI, doesn't matter. And this is where, I'm sorry, repeating myself, the power of Windows and the power of building all these components one on top of the other comes in. And I'm not done. So what do we get with VHDump? So hey, we have this cool technology that can parse files and create a virtual disk out of it. VMs use it. I want the host to use it. So we have native VHD, which reuses the same VHDump, but in this case, the native VHD simply exposes those virtual disks to the same partition. You can even boot from it. Some of you probably play with it, called boot from VHD. You can boot the physical disk, a physical machine, with VHD files. And the VHD files just loops back into the physical disk, and voila, you get another drive, but it's a virtual drive. In fact, we also have something called the shared VHDX. This was introduced brand new in Windows Server 2012 R2. Shared VHDX allows the VHD file itself to be shared across multiple virtual machines that are run on multiple hosts. And the reason it's possible is because the parsing of the VHD file, the VHDMP, has been relegated to the file server. Notice the file server is again another Windows box, so the same code exists there, and all we did was, you know what, let the parsing happen on the file server. So the output of the file server is a SCSI protocol disk that we are transferring over the SMB protocol. So we have the proxy and the filter, the parser and the filter for shared VHDX. And it goes through the same virtualization stack, gets exposed in the virtual machine. It just so happens that now multiple virtual machines can share the same shared VHDX. Sorry, I'm missing myself here. So where am I? Did something get added? There you go. Sorry, thank you. Reusing components. Whatever was available on the file server is also available on the physical machine. So we have the shared VHDX parser and the filter available on the same host so that it can run on CSV as well. So even if you don't have a file server, you can still run shared VHDX on the machine and still get resiliency. Same technology, same code base, you can mix and match and create the incredible flexible architecture that we are seeing here right now. Did it move? I'm sorry, you guys must have a really tough time following me, not finding out where the boxes are. So the final thing that I just added, if you guys notice what I meant, was the iSCSI target on the right-hand corner, right top corner. The iSCSI target is again part of the file server. It exposes itself as a target that any iSCSI initiator can connect to. The back end of the iSCSI target again is VHDump. So you have VHDs surfacing as iSCSI LANs through the iSCSI target, and again reuse of code, all the benefits that you get from the local VHDX parsing, all the benefits of VHDX are now available through all these protocols. So what we have done so far is that your iSCSI target now connects to your Ethernet cloud, and you can have your iSCSI initiator on the host or in the VM, talk to the iSCSI target, and you have completed the cycle. Your host, your physical machine can be clustered. So now you see that this existing same storage architecture just works across all these blocks. You can also have the file server being clustered, and you suddenly get a scale-out file server that's highly resilient and provides all the capabilities that you have started to expect from a highly capable storage file server, a storage system. It's fast because of RDMA. It's resilient because of its failover capability. All the connections remain alive. Now, having said all this, I still didn't have space for a bunch of technologies that's very core to storage, starting with System Center or Hyper-V Replica or the ODX or TRIM capabilities. There's bunch of technologies that keep getting added. There's a question, sir.
When you have two VMs on one host, does it have to go out on the wire to communicate with the other VM, or does it do it on the host?
So the question was, if two VMs are on a host, do they communicate by going out of the wire or staying in the box? if it's connected to the same virtual switch on the same LAN, VLAN, same subnet, then it doesn't have to go anywhere. It just communicates with it within itself. So just want to give a pause here. I took a bunch of time, wanted to go through this fairly complicated set of blocks. Didn't want to scare you off by showing it in the beginning, but it helps understand how the storage flows. So moving on, what do we really get with this kind of an architecture? Why do we care for this? And the key thing is, it's really flexible. It's extensible. This is how we were able to build the ecosystem of all the hardware vendors, all the storage vendors, provide you, the customers, the ability to do things that allows you for your unique situation. If you have fiber channel or iSCSI or Ethernet cloud or local disk, you have all the option and the flexibility. And we kept innovating in here. We introduced concepts like dedupe and VHDX and a bunch of other technologies to make sure that you get the resiliency that you expect at the lowest cost. It's scalable. It is very efficient. Things like RDMA in the protocol make sure that we are not wasting any resources, that you get the maximum performance with the lowest level of latency. With SMB multi-channel, you get the same thing with spaces and with tiering. All the innovation that we have seen so far, and we are not done. We have just started on this journey. Even though we keep claiming that it's been for 30 years, we're going down this path. It's recently that we have put renewed energy in the storage architecture. We believe that storage is definitely one of those things which are now becoming a bottleneck for any virtualized or cloud environment. So we want to put all our energy in that. Finally, it's cost effective and simple. The simplicity comes in the component that I've not shown. Hopefully some of you have attended the System Center demos, where it talks about how they can provision from bare metal, bring up complete storage infrastructure, bring up the complete physical infrastructure with a flick of a button. And that simplicity. So the entire stack is geared towards making your life easy and simple while providing with all this flexibility. So, having said that, let's take a quick recap of Windows Server 2012. What is it that we offered? And the reason why I'm doing this is mainly because I think 2012 was a bunch of new features and capabilities that got added. I keep getting customers come and tell me about, hey, help me understand how certain things work. Or I hear feature recommendation, maybe you should add certain capability in Windows, only to understand that that feature is already present in Windows Server 2012. So let me take a few minutes, walk you through some of the key highlights of what we started off with. And to begin with, let's start with the demo. And this 1 million IOPS demo is something that I love, and I really get my goosebumps when I see this happen. So let's see that again. Leah.
Thanks, Matthew. So last year at the TechEd, we showed the demo that Hyper-V in Windows Server 2012 delivered about 1 million IOPS from a single virtual machine. So why we like to show these high IOPS demos? Number one, the modern server apps absolutely has high and high IOPS requirement. And number two, to get to these 1 million IOPS levels, every component along the whole storage stack has to work extremely well. I'm going to give you a very simple example. At the mini IOPS level, a very tiny spin lock contention can easily eat up your 20% CPU cycles. So that's the reason. This high IOPS demo is the best way, we believe, to measure the quality, performance, and the scalability of our Hyper-V. So next, I'm going to show this demo. So here we have this Windows Server 2012 VM running on top of a Windows Server 2012 R2 build. Let's first check these VM settings here. So we have this like 128 gig memory for this VM. We have like 64 virtual processors for this VM. That's the maximum number of VP we support. We also have like 48 SSDs attached to this VM, and a single SCSI controller. We have 4 SCSI controllers and we support 256 devices in total. We only showed here is 48. So one of the feedback we got after we last year 1 million observers, people wanted to us to show this use 8K random reads. They say 4K random is good, but they wanted to show how about the 8K random reads. Obviously, when this IO set becomes large, our ops is going to decrease. So we have this 8K random reads. In this IO meter, we use this Q depth 32. So we have 4 IO meter processes here, and each IO meter process has like 12 threads, and each thread is working 1 disk drive. So let's see how many IOPS we can get from here. Here we go. So it may take some time to stabilize the result, but after like a few seconds, we should see pretty stable the IOPS. So we get like a 1.31, 1.32 mini IOPS from single virtual machine for 8K random reads. Just about 1 year ago, we are able to deliver 1 million. But in this server 2012 R2, the throughput is improved like 30%. So, and all the secret is help with multi-channel technologies. We introduced in Windows Server 2012, and we keep improving it in Windows Server 2012 R2. So that's the demo. Back to Matthew.
Thanks, Liang. Yeah. All right. Before I go forward, there's one thing I have to call out here. So when Liang introduced himself as a performance engineer, last year, so I'm a program manager, I decide on what features we do. Liang does make sure that it works very well and is performant and so on. To be honest, 1 million IOPS was not on our agenda for 2012. Liang was the guy who said, Matthew, let's do it, we can do it. Come on, Matthew, let's do it, let's do it. Towards the end, when we were done with features, Liang kept pestering and pestering. It was more to just stop the pestering that I said, sure, let's do it. And it has had such a tremendous impact on the crowd. Now, we know that there are not many workloads out there that need that 1 million IOPS, but the ability and the fact that we can actually do that 1 million should take away all concerns from your minds about, is my VM strong enough or powerful enough to run my mission critical workload? I think you can safely say yes. Forget 4K IOPS, you can do 8K IOPS, 30% improvement, and all because of this guy. So a big hand for Liang. So how did we do it? So not much changed in the architecture itself. So in pre-Windows Server 2012, our VM bus channel that carries the IOs from the VM to the guest, we were using 1 channel per VM. We had limited queue depth, and we had fixed VP to ensure that fixed VP for the IO interrupt handling. And in 2012, we just changed those limits. We just added 1 channel per SCSI controller or per n number of processes. The 16 is just a count over there. It could be for n number of processes. We added more than 256 queue depth per device for each SCSI controller. You do realize that each SCSI controller can have up to 4 virtual devices in them, 4 virtual disks. And we distributed the interrupt handling. So with that kind of a scale, we were able to spread the load, spread the IOs, and we could break the 1 million barrier. We got 1.3, 30% improvement. We are not done. We have not shipped yet. Hopefully, we can bump that number up again. So moving on, the other big recommendation that we had for 2012 was VHDX. We have said VHDX is the default virtual hard disk format. We created VHDX because we realized VHD was not sufficient for you guys. VHD with its limits of 2 terabyte was not enough. We wanted to build another format that was more resilient, simple enough but more resilient, better performing, better aligned with the newer hardware, especially with the 4K drives, better aligned with SANs with megabyte alignment. and better performance thanks to the variable size block sizes, or any size block size, or we wanted larger block sizes. So with all these things, including the custom metadata, the ability to introduce custom metadata, we said VHDX is the way. I know some of you are still struggling to move over from VHD to VHDX, but please keep pushing for that. We want you guys to start moving over to VHDX. Most of the innovation, as you have seen already, the shared VHDX, we are investing in VHDX. VHD works, it's great, but the future is with VHDX. We have to keep moving the ball forward. So with that, let's quickly look at some of the performance characteristics of VHDX, and Liang, back to you.
Okay, thank you, Matthew. As Matthew just mentioned, VHDX is the future. VHD belongs to legacy now. So we highly recommend every people here try VHDX. So we have a demo here to compare the performance between the VHDX and the VHD. As you know, starting from Windows Server 2012, we introduced VHDX, and we also started recommending people to use and deploy dynamic VHDX by default. One of the huge benefits of dynamic VHD is space savings. You know, space is the primary cost of this enterprise private cloud deployment. So now we are going to show two demos. One is we are trying to compare dynamic VHDX growing speed versus dynamic VHD growing speed. Our second demo is we are going to show regular performance to a fully populated dynamic VHDX to a fully populated dynamic VHD. Fully populated means all the blocks are already allocated, so that is in stabilized state. So first demo is growing speed. So we started this demo. Now imagine you want to do some backup, and the backup is ready to something like empty VHDX or VHD. So that's you have to allocate all these new blocks from scratch. So this is the VHD. We start growing VHD, and this is VHDX. We start growing VHDX. We're using two separate but identical storage, so they will not interfere with each other. You can see here, VHDX growing speed is almost 10 times faster than VHD. We can check on host. You can see here, this VHDX is kind of growing. This VHD is also growing, but the VHDX is growing much faster than VHD. So that's the demo for this part, VHDX growing speed. So next demo I'm going to show you is regular performance. That means we are going to do something like a sequential performance to this fully populated VHD and the VHDX, and see how performance looks like. So we start our meter here. So this is fully populated VHD, and here we have fully populated VHDX. They're from two different VM to different identical storage. We're using 64K sequential writes, so that's a pretty common sequential worker node at the QDEPS 128. Same here, 64K sequential rate at the 128 QDEPS. Now start the comparison here. Okay, this is regular sequential performance for this VHD, and now we're just going to start regular sequential performance for VHDX. Here we go. This is like a 40 or I think it's 40% or 50% faster than VHD. So that means when all these blocks are allocated, the regular performance of VHDX is better than VHD as well. So we can check from host as well. So you can see here, for 40 VHDX, the VHD stopped growing because all blocks are already allocated. Same thing for 40 populated dynamic VHD. All blocks are allocated, so they stopped growing. But VHDX still so much better performance than VHD for this regular performance worker node. Thank you.
Thanks, Liang. So the reason why we showed those demos and the reason why we're showing these graphs is one of the recommendations with VHDX is start using dynamic VHDX. It's definitely a lot more performant than the old VHD parser. We have added reliability and resiliency to it, so we completely support. People keep coming up and asking, what is the performance impact if I use a VHDX that's growing? You just saw what it is. It's great. So in terms of VHDX performance improvements, in terms of 1 MB sequential writes, when you compare it to a pass-through disk or a fixed disk, you see that it's very comparable. It's about 25% faster than VHDs, and it's very comparable to pass-throughs and fixed VHDs. So yet another reason why we keep saying, stop using pass-throughs. Please don't use pass-throughs. You have the option of not using fixed VHDs, but that we leave that option to you guys. In terms of 32K random writes, this is something else that we just saw. We saw that the dynamic VHD, the differencing VHD, they are about 10% faster than VHDs. Marginal, but it's still better. And then finally, the growth part. We have noticed that there's a 100% improvement when we talk about 64 KB queue depth of 64 non-buffered 64 KB writes, and 800%. Actually, what you saw was 1,000% improvement, 10x improvement when we had non-buffered I/O with 16 MB at queue depth of 48. So what did we finally say in Windows Server 2012? What was our recommendation? We said move away from pass-through. Let me repeat, move away from pass-through. You don't get the benefits that you used to get. It takes a while for people to get this, but start moving away from it so that you can take advantage of all the innovation that's happening in VHD, VHDX. Files help you. Files are your friends. It's good. Start using dynamic VHDX. And then finally, and this is where the interesting controversy starts, is it centralized storage or is it decentralized storage? Should we have local drives, local disks, or should we have central SAN kind of infrastructure? With all the discussions we have had with customers, our own internal testing, what we have come to the realization is that if it's a fairly small one host, two host deployment, maybe you're okay with having local disks, but any largest deployment, the centralized storage is what works best in terms of economy, in terms of scale and performance, in terms of resiliency for the storage. So from that point of view, we keep saying decouple your storage and compute. You also have a better handle on what kind of resources you're allocating to your virtual machines. You can very easily separate out your tenant resource utilization from your host resource utilization. So any questions so far before we move over to 2012 R2? Maybe not. All right. So 2012 R2. You guys actually saw a bunch of these recommendations. Hopefully you have seen Ben's and Jeff's sessions on when he talked about when they talked about what was new in 2012. If not, please definitely go look it up. MDCB 330, that was Ben's talk about what's new in Hyper-V. We will touch upon a couple of those things. So starting with VHDX online resize. So that's one of the cool new features that we have added. In fact, it's not cool because we actually finally heard you guys. We have been hearing from you that you needed it, and we have been dragging our feet. So finally in R2, I admit, we said, yeah, we need to do it, and we did it. And thank you very much for really appreciating what we have done. It's no magician's trick. We should have done it from the beginning, but there you go. We have it. So it's complete resize. We grow the VHDX, and we shrink it. And shrink is a safe operation. If you have data, then we will not shrink beyond it. It's for VHDX only. It only supports SCSI. And with the Generation 2 virtual machines, you can have this on your boot drives as well. Now let's get the demo. Let's see how it works.
Cool. As Matthew mentioned, VHDX online resize actually is one of the top feature requests from our customers. So we made it happen in Windows Server 2012 R2s. I'm going to show demos here. So in this VM, running on top of Windows Server 2012 R2 build, we have this VHDX is only 10 gig. So we are trying to expand it. The reason we want to expand is people don't know how big they want their data drive to be, So from time to time, they want to increase or probably reduce the size, but they do not want to shut down the VM because their server workload is running. There should be no down times here. So online research can help customers do this without shutting down VMs. So we're going to show demo. So first thing is, we know VHDX support up to 64 terabytes. So one day, Odmin want to say, hey, I want to create the largest VHDX in the world. Okay, we only have 10 gig. Let's do it. You see that? Instantly, your VHDX inside the VM grows to 64 terabytes, and your VM is still running. After some time, you say your VM told Odmin, hey, I don't need that. That's just too big for us. I wanted to go back to like 2 terabytes. No problems. It becomes 2 terabytes instantly. So everything happens instantly. And the cool thing is, if you don't know what's your safe smallest size, you can just do to minimum size. And then we instantly shrink your VHDX inside the VM to smallest but safe size. So you have no data loss, everything is safe. And if people try to reduce size beyond that safe point, say, I wanted to reduce 6 gig. Is that safe? No, because if you look at that, this data drive is formatted with 10 gig. So you have to free some space first. But if you try to do these risky operations, something is going to happen. We will not allow you to do that. So everything is kept safe and very flexible. Thanks. Matthew.
Thanks, Liang. Okay, so that was VHDX online resize. The story behind it is the reason why we have both expand and shrink is to make sure that as a hoster or your IT providing value to your customers, you have the flexibility to handle your customers' requests. Your customer might not know what they want at the time of initial provisioning. They might ask for too big or too small, and you have now the flexibility to increase it or decrease it safely. Next topic, storage quality of service with an asterisk. It's not complete. We have still work to do, but what we have is complete in terms of what we are providing right now. But there's more work to be done. So let's see, what have we provided in R2? We have the capability of limiting IOs. So you can say for a specific VM, you don't want to give any more than, say, 100 or 1,000 IOPS. That's your limit. That's the maximum that the virtual machine will get. You have the ability to set a reserve that it should get a minimum of 100 or 200 or 1,000 IOPS. We can do that. But this is where it gets interesting. When you set a reserve, you're guaranteeing, and like all of you know that you can never guarantee storage IOPS. You never know what's going to happen at the back end. You believe that you have the excess capacity to be able to guarantee that, but some other rogue process can come in and steal your IOPS. Maybe there's a disk corruption or crash, something else, or some other bugs that can crop in and suck away your IOPS, so you can never guarantee it. So when we talk about reserves, we talk about best effort to make sure that we can throttle the IOs to give the reserves to the right VMs. But failing that, we will start giving alerts. And the alerts are the key thing here. We give you events that you can monitor and make sure you take corrective or preventive action to ensure that your system functions the way it was designed to function. And then finally, we have provided new metrics, the way to measure these attributes. So before I keep going, let's go to another demo. We talk about storage cores, and let's see.
All right. So next we are going to show a cost demo. So we are going to have two demos here. One is like a cost limit. So that means we now in Windows Server 2012 R2, we are able to limit how many maximum IOPS each VM can deliver. Second demo is show cost resolve. That means we can make sure each VM deliver minimum number of IOPS. If they do not, we are going to fire up events to alert the system admin. So this is the first demo. So we have two VMs here. So first VM, we call it like a good guy. You know, good guy has good citizens. So always enjoy his regular and expected throughput. As always, he's happy. Everything is happy. So we get that to almost 200,000 IOPS. Now, bad guys come in. What the bad guy typically does, he uses like a very small IOs, say 1K random. This is for SSD. For HDD, he probably uses like a 5 terabytes sequential reads. So he uses extremely high queue depth, 256. So this is bad guy come in, he say, hey, I want to steal all this bandwidth from you. Let's see. So bad guy started his workload. And instantly you see the good guy's throughput dropped 50%. So good guy started complaining. That's not good. I want to get back my performance. So sister admin take actions here. Hey, bad guy, you cannot go more than 1,000 IOPS. So we have this feature called QoS, quality of service. We limit this to 1,000 IOPS. So that's the maximum bad guy can get here. And instantly, you see the bad guy is capped at 1,000 IOPS precisely. Suddenly there is some like a margin here. And the good guy get all his good performance back. So he's very happy. So next, I'm going to show a cost resolve demos here. So we have cost resolve. Suddenly he's a good guy. Okay. The purpose of resolve is we wanted to make sure this VM delivered at least that the number of IOPS. If not, system must file an event to alert the system admin, hey, that VM workload is in degraded status. Okay, let's start this cost resolve VM demos with nothing set. So we do not set any resolve. So we get like 13 these IOPS. Now, if VM system admin come and he say, hey, I wanted to check if you can deliver like 200,000 IOPS. Obviously, he cannot meet that resolves. And we set a maximum to 400,000. I said 2 minutes. Let's see. We just set a ridiculous high. We know he cannot meet that. So within 16 seconds, our event is going to fire up. And the system admin will be get notified. So we have like 60 seconds, like a window here to trigger this event. So we should see in 60 seconds, the system start to report, hey, that VM is in degraded state. So you need to either take some actions or just change your resolve to some like more realistic goals. Let's just wait. So after we trigger these events, we can set up to a more realistic goal. And the more realistic goal, we also trigger another event to say, hey, that VM is back in normal status. We have to wait. So just double check and set this correctly. Yep. Here we go. Actually, yep, we have events filled up. So I'll show you. See here, the primordial pool has said this event triggered for this primordial pool says we have detected this degraded quality of service. Please do something properly. So now system may think, maybe that's just too high. Let's set it to 100,000, just to make sure it's more realistic goals. And the maximum is 200,000. So we know that the VM can be happy with this 100,000 minimum IOPS because it can be 30% more than net minimum. So we should see another event. Here we go. We have a second event filled up. And if we clear this detailed information, it says, hey, that VM is back in satisfactory quality of service. So this can help your admin to dynamically adjust the quality of service of VMs to allocate the resource properly, and every VM will be happy. Thank you, Matthew. Back to you.
Thanks, Liang. So what we just saw, we were talking about limits of how to cap someone else's IOPS or the reserves. The main thing that we saw in the demo was how the events get generated when you can't satisfy the need. We also have something else in the system which actually balances the I/O and throttles it, but that throttling at this point only works on a single host. So if you have multiple virtual machines, it will try to balance out the I/Os to ensure that it gives the minimum reserves to the VMs based on the settings. But if your storage is residing somewhere else, like on a file server, there can be other events, other virtual machines running on other hosts that can suck up that storage capacity, and that's where those events come in. So going forward, our investment will actually be in those to make sure how can we take the throttling out of a single host and spread it across multiple hosts so we can balance it across a bunch of hosts or at the storage level. But regardless of whether we do that or not, the key thing is we will never be able to bring it down to a level where we can give more capacity than what the storage actually has. So as admins, you guys can always configure more, as Liang showed, more than what the storage can deliver. And that's where the events come in. The events will help you figure out that, hey, my system is not performing optimally. Let me try to take corrective action and before the customer starts complaining. So let me introduce you to a concept of normalized IOPS, and this is how we measure limits. You guys know that I/O is not I/O, as not all I/Os are equal. And when you're trying to do limits or counts, or when you're trying to set these kind of limits, how do we determine how to cap it? So we came up with this concept called the normalized IOPS. And what normalized IOPS means is that we say, assume all I/O is 8K. And then we'll start counting as 8K I/Os or multiples of 8K I/Os. Remember, this is only for accounting. So if the incoming I/O is greater than 8K, we do not split it. The I/O is not really split. We just count it as more. So in this particular example, what we are saying is an 8K I/O, a real physical 8K I/O, will be counted as one normalized I/O. A 4K, anything less than 8K, will also be counted as one normalized I/O. Anything greater than 8K will be counted as a multiple of 8Ks. So if it were a 10K I/O that came in, the 10K I/O will go through, but we'll count as two normalized I/Os. If it were 16K, we would still count it as two. 20K, 3. So that's how we start counting it, and the limits are based on that. We determine our limits and cap it based on that. And we use this, and I'll show it to you. We use this technique inside the store VSP. If you remember from the earlier diagram that we had, the store VSC is what lives in the virtual machine. The store VSP is on the host. So we apply the limits on the host. The limiter lives as part of the store VSP, and we are able to cut it down. Talking about the reserves, if I can, yes. The reserves and limits, they are both set for each virtual disk. It's not at the VM level. You can go to each virtual disk and set its own reserves and limits. Threshold alerts are created, and these thresholds or this balancing is actually done on the VHDMP. Notice it's still on the host, but the balancing and the reserves is actually being handled by the VHDMP parser. Now, some of you might have heard or read that we have always had this thing called the I/O balancer. It's been there for the last few releases. I/O balancer ensured that there was fairness. We never put weights in there. We ensured that if there are 10 VMs running and all 10 of those VMs will get I/O requests go through, even if one was exceedingly high. So we balanced it out such that none of the VMs were starved. We have reused that I/O balancer, enhanced it, and that's where we've added our reserves. So the VHDMP, again, it balances the I/O, it throttles VMs that should not have more so that the reserves can be met. If the reserves are not being met, then we generate events. Once we have cleared the condition, we automatically send another event to clear that event. And the third thing, storage cause metrics. Typically, you use metrics for chargeback. We have added a few more metrics. The average normalized IOPS, the average latency. These are a point in time number or value that you can get at any instant. It just averages out or weighted averages out over the last 20 seconds. The aggregate data written and aggregate data read is when you start and stop your metrics. And then let me quickly go through a bunch of other capabilities that have been added. I talked a bit about shared VHDX. You will get more details in the session that I have listed out below, the MDC B311. Please attend that to learn more about it. Shared VHDX is where the virtual machine sees a shared SAS disk. It's just backed by VHDX. The benefits are tremendous because now as an IT admin, you do not have to expose your storage infrastructure into the virtual machine. Earlier you had to use iSCSI or Fiber Channel, which exposes your storage. Now you can just deal with everything as a VHD file or as file based, so you can separate out your tenant data from your host data. And yes, so please attend that session. I will rush through it. We have 17 minutes left, so a couple more slides to go through to bring you up to all the other innovations that's happening. Spaces, again, there's another session, exceptional IOPS. Please attend that to get more in-depth about how Spaces work, specifically how the tiered storage in there works. So tiered storage had two parts to it. The first part was how you can have SSDs in front of your spinning media. Here the activities are measured in the background. They move the hot data to the SSDs. It happens in the background, and you get the benefits over time. The cold data gets moved to the hard drive tier. So tiering is automatic. You don't have to worry about it. In fact, as an IT admin, if you prefer, you can explicitly assign files to the hot areas as well. Yes. So the question was, how often does the hot and cold area swapping happen? Actually, I don't know the exact number. What I've seen and observed is that over a couple of days, as you keep running these, like specifically for our demos, as when we have this, you start noticing that your demos start getting faster. So I want to say it's at like minutes or hourly granularity. It's definitely not in milliseconds or seconds, but I might be lying if I said I know the exact answer. The write-back cache, it complements your SSD tier, what you had. The write-back cache is excellent because it absorbs short bursts of high-intensity writes. Those writes are captured on the SSD and then eventually written down to the hard drive. So it's great if you have a bursty kind of environment. The advantage of these kind of technologies is that they just blend in with the virtualized storage stack. You have these capabilities on the file server. your VMs start behaving and performing much faster without you having done anything. And then finally, we have live deduplication. So live deduplication is something. So deduplication was introduced in 2012. Deduplication, what it does is it takes the common blocks in files. It's a file filter. It lives on the file server. It takes the common blocks and then aggregates it such that any access to any of the files to that particular common block goes to a single point. Now, it's great as a space-saving entity. It provides great space savings. Your capacity, especially if your drive is filled with VHDs, specifically system OS disks, you will find significant savings. We have seen anywhere from 90 to 95% savings in VMM libraries where most of the images were just Windows images. So you get a lot of benefit, and that was 2012. In R2, we introduced that to have live virtual machines. So in 2012, you could not have live virtual machines hanging off of the deduped partition or deduped volume. In R2, we made it live. But even in R2, we have limited it to VDI. And that's a common question I kept getting asked. Why just VDI? Why not for every workload? It's Windows. It should just work. And the main reason why we have limited is nothing to do with technology. It's to do with we just had a year. There's a bunch of perf tuning that needs to be done, especially when we start thinking of what kind of storage requirements are there in virtual machines in serverland. In VDI, it's fairly homogeneous. The I/O requirements of a VDI workload can fairly easily be characterized. So we felt comfortable based on our testing that the benefits that we get is tremendous. I'm not sure if you guys saw one of the demos that Jeff had where a deduped volume, so VDI or VMs coming off of deduped volumes actually exceeded performance even more than if it were non-deduped. So dedupe, while being capacity savings, it's also performance enhancing. When you combine that with write-back caching and hot areas, your performance goes through the roof. You are no longer constrained by your storage system or spinning media. None of those bottlenecks exist. Again, this is one of those technology areas where we are fairly committing that we have gone down this path and we'll keep innovating and make it easier, cheaper for you to get that just right out of the box. So this dedupe is available only on the file server. The file server can have CSV on the back end, so dedupe works with CSVs as well. It's not expected to work well. Okay, I take it back. It can work on local Hyper-V host. It's not recommended. Technically, there's nothing preventing it. As we said, we are recommending and pushing people towards centralized storage. Dedupe does take use of CPU and memory as it tries to grovel in the background, find common blocks, and combine them. So there is activity happening. There's disk activity, CPU and memory activity. You do not want that kind of an activity happening on your Hyper-V host. It can kick in at any time, and it might take away valuable resources from your VMs. So please do not try to attempt it. But if you're experimenting, you have 2 machines or 1 machine, you just want to play with it, go for it. Set up a file server and do those things. But please do not deploy it in production as such. So finally, what are we recommending? And please take all this with maybe a pinch, grain of salt or whatever. I understand. I started this whole premise saying that the customer's needs, your needs are varied. But I've also had people come and ask me, so what if I don't have any requirements, if I don't have any history, no baggage, what should I deploy? And we always go back to saying, don't know, try to do something. And so now we want to put a foot on the ground and start recommending something. Again, if you're not following this, it's okay. We support a bunch of configurations. So let's start with the huge architecture thing that we drew earlier, saying, this is everything that we support. It works great. You start asking me, so what should I do? My first answer is try to please make it as simple as possible. Go with the simplest thing. What is it that you really need? If Windows can help you do that with all Windows components, System Center to manage it, if you find that being usable, then stick with it. Start adding more capabilities into your storage stack, into your networking stack, as you find the needs to improve on that. If your workload or your application needs something specific, like high performance networking, go with SRIOB. Until then, you don't need to. With all the switch extensions, do you need it? Maybe, maybe not. But try to go for the simplest denomination that will keep your deployment simple. So what is it that we really recommend? Let's take out a bunch of those things. I probably would not recommend Fiber Channel if you never had it in the beginning. Go with a simple JBoard architecture. Have a file server, that's just a Windows box. Make it clustered. Clustering is easy. It's the same clustering that works on the file server as it works on your Hyper-V host. Have spaces on the file server. You don't need spaces on the Hyper-V host. It's all centralized. Use just dynamic VHDXs. Now, I have generation 1 virtual machines here, but as you start going forward, I will even have a recommendation which says just go generation 2 virtual machines. But for now, generation 1 is the norm, and that's the default, so we'll stick to that. I would like to get rid of all the legacy parts in here. Make it simple. The shared VHDX option, keep it on the file server. You don't need that as a CSV on the Hyper-V host. So this is a recommendation. The Uber point here is just try to keep it simple. Just because we give the flexibility, we have given you a loaded gun, let's not just use all the technology that's available. There are some specific folks out there who have specialized needs. You will need certain deployments. You will need the SAN. You will need Fiber Channel. And that's okay. And we work with it. And we have great relationships with our vendors, with our partners to enable you to do all that. So with that, let me summarize what we have just done. We take storage very seriously, especially when we start talking about virtualization. We understand your pain. We know that storage is expensive as it stands today, and the needs for your storage infrastructure is just going to keep growing. As you get into cloud, as you get into larger deployments, storage becomes a bottleneck, and we keep investing in that. We try to make it faster, more resilient, cheaper. And any other adjectives you can add to it, we do all that. And we will keep innovating. We have been innovating, and we will keep innovating to provide you with the best possible experience that you can ever hope for. And we'll keep doing that because we believe that's one of those areas, along with compute and networking, where you guys feel the pinch. So with that, I can actually take you to questions, but here are all the related contents. This time in TechEd, I have noticed that we have a lot of storage sessions. So please feel free to attend some of them. I will be at the booths and Liang will be at the booths. Please come by, talk to us if you have specific questions. We would love to talk about storage in specific, Hyper-V in general, anything you want. It's always fun. Even if you don't have questions, do come by, talk to us, because we would love to hear from you. I know some of the things, or most of the features that we kept adding is based on feedback from you. You guys come in, explain your needs, your pain points, and we start internalizing it. You hear it once, twice, 10 times, and you say, maybe that's really a problem. We should fix something. Online VHDX expand, that's one of those few things that, yeah, we heard you. And definitely there's more, and we would love to hear from you. So, final few things, housekeeping things, track resources, learn more about, there's more resources, and I'm sure you guys are sick and tired of seeing these slides. Complete an evaluation. Please, I would love to hear how Liang and I did. So please do fill out your evaluations. We want to keep improving, so the next time we are out on the stage, we give a better presentation and talk about more relevant topics. And yes, evaluate the session. And that's about it. Thank you, guys.
Thank you.